Results from single-dish telescopes like Herschel, the JCMT, Nobuyama, IRAM, and so on can greatly strengthen an ALMA proposal, but converting those observations into a sensitivity estimation for ALMA is not always straightforward. A complete and rigorous treatment to convert observations from one telescope to another can be tricky, involving antenna patterns, source coupling, and other factors. For a full discussion, you can consult online documentation available from summer school programs provided by, for example, NRAO or IRAM. Fortunately, if we just need to use these single-dish results to estimate ALMA sensitivities, we can use some simple approximations. Suppose your single-dish observation was presented in Janskys per beam, which is the flux density of the source measured within the telescope's beam. To estimate the flux density within ALMA's usually much smaller beam, you'll need an estimate of the angular size of the source. If the source is small compared to the ALMA beam, for example, then all of the flux will fit into the beam. You're basically done. You now know the expected flux density for an ALMA observation, and you just need to decide on the signal-to-noise ratio you need. But what if you know, or have reason to believe, that the source is bigger than the ALMA synthesized beam? Let's look at an example. Suppose you have a CSO observation of a sub-millimetre galaxy and have measured a flux density of 32 millijanskys within the CSO beam. From other evidence, you believe that the angular size of the galaxy is about 2 arcseconds, and you'd like to observe it with ALMA at an angular resolution of half an arcsecond. That 2 arcsecond wide galaxy is now 4 ALMA beams wide, or 16 ALMA beams in area. This would mean that 32 millijanskys measured by the CSO beam was spread across 16 ALMA beams. The expected flux density in the ALMA beam would thus be only 2 millijanskys per beam. If you wanted a 5 sigma detection, you'd need a sensitivity of 0.4 millijanskys per beam. Observations from single-dish telescopes, particularly spectral data, are often quoted in units of kelvins, or kelvins kilometer per second, which is the integrated intensity over a spectral line. The simplest, if not most rigorous way to use an antenna temperature to estimate an ALMA observation is first to convert the antenna temperature into a flux density using the point source approximation, usually written like this, where this is the integrated intensity in kelvins kilometer per second, this is the flux density, and this is the effective area of the antenna surface of the single-dish telescope, equal to the area of the antenna, pi r squared, times the overall aperture efficiency. You should be able to find out the aperture efficiency from documentation for the single-dish telescope in question. Armed with this approximation, we're now ready to convert our integrated intensity into a flux density. Plugging in the appropriate values and constants, the conversion factor simplifies to this, where d is the diameter of the single-dish telescope in meters, and eta sub a is the aperture efficiency. Let's try an example. Suppose we had an IRAM 30-meter telescope observation of a nearby galaxy and detected a 220 kilometer wide CO2-to-1 line with an integrated intensity of 22 Kelvin kilometer per second. Now IRAM has an antenna diameter of 30 meters and, checking the IRAM website, an aperture efficiency of about 0.45 at 230 gigahertz. Plugging these values into the point source approximation, we find that the measured flux density is 191 Janskys kilometer per second per beam. Dividing by the line width, and noting that the line is relatively flat, the average intensity of the line is about 0.9 Janskys per beam. Let's observe it with ALMA at an angular resolution of 1 arcsecond. What flux density would we expect in a 1 arcsecond ALMA beam? Well, as we found before, that depends on how large the source is. In the worst case, the emission is spread evenly over the 11 arcsecond IRAM beam, or over 121 ALMA beams. In this case, the expected flux density would be about 7 millijanskys per beam, A 10 sigma detection per spectral channel would require a sensitivity of 0.7 millijanskis per beam. Conversely, if the source were only 1 arcsecond or smaller in size, the expected flux density would be the full 0.9 janskis per beam. A 10 sigma detection of line emission per channel would require a sensitivity of 90 millijanskis per beam. As you can see, knowledge of the apparent angular structure of your target source is crucial in order to estimate the sensitivity and hence integration time for an ALMA observation. In some cases, you simply will not know this before getting ALMA data. In the absence of other data, or a solid physical argument that leads you to expect a particular range of angular sizes, it's probably a good idea to make the most conservative assumption that the source fills the single dish beam. In any case, be sure to explain fully in your technical justification how you estimated the required sensitivity.